Hi, Chemistry 12-2. Welcome to Unit 3. We're going into Unit 3. It's going to involve some acids and bases, and we're going to be working on it throughout week 5, 6, and 7. It's very closely intertwined with Unit 2, Equilibrium. So the first video this week is actually a quick review of equilibrium and some of the topics we talked about in that unit, because we really need a pretty strong working knowledge of those things to move forward into acids and bases. Okay? The first thing we want to talk about, and if you want to pause right now and go and get some paper and pencil and calculator, we are going to be doing some calculations in these videos, so sometimes it's nice to pause and figure out something first before you take a look or listen to how I calculate it, and therefore you can kind of learn from your mistakes. So pause now, pick up the materials you need, and then come on back. All right, welcome back. So if you're looking here, we've got section 19.3, and that's the section we're going to be covering in this video from your chapter. We're going to talk about the strengths of acids and bases. We're going to kind of concentrate on acids for this video, and we'll take a look at bases for the second video. We know a little bit about acids and bases right away, but let's just concentrate on acids first. So we have our strong acids and our weak acids. And what are some differences? Because that's really what we want to get out of this video. We're going to take a look at two different ways that we can actually measure how strong or how weak an acid is. Okay? So strong acids, you'll see right off the bat that they have a low pH. So that's meaning, you know, the pH scale from 0 to 14. So we're talking about strong acids being down there at 0, 1, and 2. Remember, the pH is parts per millions of hydrogen, so it's a lot of hydrogens are going to give you that low pH. Opposite over here for weak acids, not up into the teens, like 10 and 11. We still want it to be below 7 because it's acidic. And remember, acidic solutions, the H positive is greater than the OH negative. So we're going to be below 7, and usually 6 or 5 for weak acids. A term we used in grade 11 is electrolytes. Electrolytes is a solution that will conduct electricity. And in order for a solution to conduct electricity, it needs to have charged particles or ions. So strong acids are strong electrolytes because they produce a lot of ions. They actually ionize quantitatively. And the term ionization means to take an acid or a base, usually an acid with the term ionization, and to break it up into its ions. It's 99% yield. So when you look at the equation, an HCl is a strong acid. So when you take a look at the HCl here, see how we have one arrow? It's a quantitative reaction. So 100 molecules of those, they're all going to break up into H positives and Cl negatives. Over here on the weak side, you can see the ionization is different, and that's the biggest key between strong and weak acids. It's their difference in ability to ionize. Strong acids ionize completely, weak acids do not. It's less than 50%. Here we have acetic acid, right? So vinegar, and it's got a percent yield of 1.3. So it definitely has equilibrium arrows. Reactants are definitely favored, not the products. And you can see we have just a small or a lower amount of charged particles. So it's not as great an electrolyte as a strong acid will be. So the general thing we know so far moving forward is that strong acids completely ionize in an aqueous solution, and weak acids only slightly ionize in an aqueous solution. So they both ionize, but the degree of ionization, the degree of their separation is what's important. We've seen these formulas before, right? So in the last unit, we talked about Kw, pH, pOH. This is a new one, so we're going to take a look at this one during this video. And we're going to take a look at this over here. So Ka, how to find the Ka, and what's it tell us? Here, how to find percent ionization, and what's it tell us? Both of them are going to link back to the strength of acids. So how to communicate the strength of acids? Two ways. One, percent ionization. We'll take a quick look at that, and then we'll spend most of our time on Ka, so finding the acid ionizing acid constant. You can use the symbol P for percent ionization. Some people will just write percent ionization right here. And it's very similar to something we've talked about already. So we've talked about percent reaction, we've talked about percent yield, and so percent ionization is exactly the same thing. How many products are we making, right? Is it ionizing completely so that all of the molecules are breaking up into their ions when they're put into water, or is it only slightly ionizing? That's what this is going to tell us, this percent. So strong acids have 100% or 99% ionization. Weak acids, it's a lot lower. Let's take a quick look. How can we, it's really just a ratio. So how can we calculate the ionization constant? So here it says, and maybe I'll shut this so that you don't have to look at everything at once. So the question here says, the pH of a 0.10 mole per liter methanoic acid solution is 2.38. Calculate the percent ionization of methanoic acid. Okay? And so when we want to look at percent yield, we're really comparing reactants and products. Did we make a lot of products or did we make very little product? And so you can see by the formula up here, we want to know, so this is a product, just kind of like always the ratios we've been looking at with KEQ. Here we've got our products on the top and we've got our reactants on the bottom. And we're not worried about the negative ion, we're just looking at the positive ion because ionization really goes with acids. And acids are all about releasing, right, a hydrogen ion or a hydronium ion. So that's the amount we're looking at. So it's the amount of H positive compared to, and this is a symbol we see quite often, a capital H and a capital A. It's for an acid. We know that most acids, not all, but most acids start with an H or end with a COOH. And so this is a very quick general equation or general symbol we can use for an acid, capital H, capital A. Some people actually write the word acid here in the formula. So we need to find the H positive, we need to know the concentration of our starting solution, multiplying it by 100 turns it into a percentage. So here we are looking for, they've given us a couple things. What have they given us? And so if you, I just have my airliner here. So they've given us, if I can find my cursor, forget it. I don't have time to fight with that today. So if we underline this right here, that's going to be important, and this right here. So they've given us a couple pieces of information. They've told us that methanoic acid has a starting solution of that, and they told us that when the methanoic acid is placed in water, the water creates or has a pH of 2.38. So from our last unit, we know that pH is going to be very helpful because it's going to allow us to find that first part of the puzzle up here, the H positive. And the bottom part of the puzzle is going to be this. So the concentration of your acid is your HA, and we don't have the H positive directly, but they have told me the pH. So from the last unit, I can take that pH and find my H positive. So if we continue down here, and here we go. So we're looking for our H positive concentration, and some people are having some difficulties using these different formulas. So we talked about that briefly last Thursday. Here's another way of looking at it, and this might be more helpful to you with your calculator. You can use 10 to the x or y to the x. 10 to the x tends to be the shift or the inverse of log. And so 10 to the negative pH, right? And I don't know why I have 3.48 here, because our pH is actually 2.38. Right, but gosh darn it, 3.8. Okay, and so we can plug that into our calculator and find our H positive. Here's the old standby, and some people have been confused by this dividing by log, because you're right, if you try to divide by log on your calculator, it's not going to happen. So you can look at it a different way. What we can do is, if we want to highlight, cooperate with me, if we want to highlight this, and we can get rid of it. All right, just cross that out. And what happens is, instead of dividing by log, you can just take the inverse. My patience is low when it comes to these things. You can take the inverse log. So if you want to look at it this way, that works as well. So negative pH, inverse log. So it might be shift log, right? So the shift button or the second function button or the inverse button, that will work for you as well. Make sure you put the negative there, okay? So when we do that, we can come up with our H positive concentration. And our H positive concentration works out to be 4.2 times 10 to the negative 3. So when you find this, when you do this, you get 4.2 times 10 to the negative 3 molars. It's a concentration, so be careful with your units. You want to put molars there. So our H positive works out to be 4.2 times 10 to the negative 3 molars. Our HCOOH, that's the symbol for methanoic acid, and they told us was 0.10 molars. So when we divide that and multiply by 100, we get 4.2. So 4.2% ionization. Okay, what's that telling me about methanoic acid? It's telling me something about methanoic acid. So 4.2, it's lower than 50, right? 50 is our benchmark. It's lower than 50. It means that only 4.2% of these ions are being, of these molecules are breaking up into their ions. So this is an example of a weak acid. Okay. Um, Here it says, remember, percent ionization only predicts accurately within a narrow range around a specific concentration for an acid, for example, 0.1 molars. This is not the best method of determining if an acid is strong or weak because it's limited. When we're looking for percent ionization, it's only really possible to find the percent ionization if you have a concentration of 0.1 moles per liter. So it's very limited. It works great and it's very accurate if your concentration is 0.1 moles per liter. But if you venture off into a higher concentration or a lower concentration, your percent ionization is not always accurate. Okay, so just be aware of that. The next thing I want to talk about is Ka. So this is the second way of coming up with, or I shouldn't say coming up, determining the strength of an acid. So you can look at the percent ionization, and that does work, but it does have its limitations. So it is kind of assuming your concentration's 0.1 molar. What if your concentration isn't? So what's a better or a more diverse way of calculating or looking at quantifying the strength of acids? And this is our go-to, and it's called Ka. So the ionization constant for acids. So ionization constant, that's because we're ionizing our acid into its ion. So ionization constant for acids, that's what Ka stands for. It's basically KEQ for acids. So we're going to take a look at a question here. It says the strength of an acid can also be communicated using an equilibrium constant. So you can use percent ionization, but it's got limitations. So what's a second way of finding the strength of acids? And that's finding your Ka, or looking at your Ka. Once you find your Ka, it'll tell you a little bit about the strength of your acid. And so it's a glorified equilibrium constant. So we're going to take a look at that. All right. What we have here is acetic acid. So here's our acetic acid right here. And we have looked at it already. We know its percent ionization, it's 1.3. And we know that this guy is going to ionize, not a lot of them, right? Only if you had 100 molecules of this guy, only one, not even 1.5, only one will ionize and break into H positives and CH3COO negatives. So the anion and the cation, okay? I wanted to show you and talk very quickly about this picture here. This is actually a structural diagram for acetic acid. And you can see that we have lots of H's. So often people are like, which H is leaving when you talk about acetic acid? And so you have to think about, and we're going back to grade 11 again, but you have to think about your covalent and your ionic bonds, okay? And when you look at covalent and ionic bonds, what you find is that the covalent bonds are all about sharing, and the ionic bonds are all about taking away, right? So an exchange of electrons, as opposed to, this should be easier than it is. There we go. Awesome. There. Oh, golly. So what happens is you look here, and you can see this carbon has 3 hydrogens on it. And this carbon is representing this carbon right here. And see how the H3 is right beside it? So instead of writing it C2H4O2, they've written it in this structural format so that you have a hint of how these atoms attach together. So carbon has 3 hydrogens, and they're covalent bonds. And then this carbon, there's a covalent bond holding these 2 carbons together. These are the ionic bonds over here. So there's a double bond to an oxygen, and then there's a single bond to an oxygen, which is bonded to a hydrogen. So there's a little ionic bond between the oxygen and the hydrogen. So what I was trying to do, and failing horribly, was to try and get a circle here, and then try and make this circle bigger, and then trying to turn that circle into a red circle. Bear with me. And show you or outline that it's actually this hydrogen that leaves. This is the hydrogen that leaves, okay? This is a very ionic equation, or a bond rather, and so when we are going to split apart, so this is the CH3COO, that's this part here, and the H is this part here. So you can see they split apart, these being covalent bonds, the hydrogen stick. It's this hydrogen bond down here. And notice the charge. That's going to be important moving forward. This guy, he's a proton, he's got a positive charge, but when he leaves, it leaves this whole anion with a negative charge. So there's a negative charge there, okay? So just to kind of keep talking about what's happening with the reaction. So we want to find the Ka, and I said the Ka is just like Keq. So we know from our former unit that Keq is your products over your reactant. And it's still true for Ka. So Ka, like I said, glorified, right? Your products over your reactants. And when we plug in our concentrations, if we wanted to, we could come up with a Ka of 1.8 times 10 to the negative 5. Now that comes from a table that I'm going to introduce to you today, and it is in files on the team site for week 5, and it's really important. You want to make sure you're okay. Notice if we look at the units, this is in molars, this is in molars, this is in molars. So it would be molars squared over molars, or moles per liter. So there is technically a unit when it comes to Ka, like there was for Kw, but the IUPAC, if you remember IUPAC, the International Union of Pure and Applied Chemistry, they have actually ruled in saying that we should not use units for Ka. So Ka and Kb will not have any units, even though if you kind of factor out your units, it actually does have units, right? Moles per liter. We're going to ignore those units, so we're not going to put any units on for our Ka and our Kb. All right, molars for concentrations, but Ka and Kb, no units. So if we review, Keq, no units. Kw have units, molar squared. And Ka and Kb, no units. So the general formula here, and you might say, well, Ms. Ryan, that looks a little different. The general formula here for Ka, if you want to stop now and write this down, or if you've had like maybe a running piece of paper that you've been writing down these formulas, this would be a good formula to write down. If you want to find the Ka, right, H positive squared. Now, how come I can do that? How come I don't have to put both products here? Well, we'll talk about it a little later, but you can see this is stoichiometric, so 1 to 1 to 1. So this has two ions. When it breaks up, we get one of each. So these guys will always have equal concentrations. So if I know the concentration of H+, I can just square it, because the concentration of CH3COO negative would be exactly the same, okay? So when we write out our general formula for Ka, we just say, listen, I need to know my H pluses because I know my other ion will be the same. So we say H positive squared. And we need to know that that equilibrium concentration for your acid. So before it starts to break up, what's its concentration? And then when it breaks up, how many H positives? So it's a quick ratio between products and reactants. How much product, how much reactant? And then you can get your Ka. Now, how does the Ka help? The Ka helps because just like Keq, remember Keq, our benchmark was 1. So if Keq was greater than 1, the products were favored. And if Keq was less than 1, the reactants are favored. It's the same with Ka. Ka, if your Ka is greater than 1, you have products being favored, and you're going to have a strong, strong acid, right? If the products are favored, it means you're making lots of ions. So the ionization is 99%. So you'll have a very strong acid if you have a Ka greater than 1. If you have a Ka less than 1, then your reactants are favored. So you're not going to have, you might have a medium acid, not a strong acid, maybe a medium acid, a little less weak. If we take a moment here, I wanted to show you this acid-base table and tell you a little bit about this acid-base table. The acid-base table here, you can see we have a few columns here. The first column is percent reaction. Another name for that would be percent ionization. So they're telling us the percent ionization for different acids. So it's called an acid-base table. And In this column here, we have acids, and over here we have conjugate bases, and we'll talk more about what a conjugate base is later on. So we have the name written out, and we have the formula beside it. So this is also a good cheat sheet if you have to, or if you've forgotten the chemical equation, or rather the chemical formula for an acid. You can always go back to this table because there's tons of acids listed here, and their chemical formulas listed beside them. The two columns over here, the first one, like I said, percent ionization, percent reaction. And you'll notice there's only 6 that have 100% ionization. And they're known as our 6 strong acids. So if you want to pause right now, this is probably something to know. Here are the 6 strongest acids. They're the only strong acids that we have. And they will have 100% or 99% ionization all the time. So it's really good to be aware of that. Sulfuric acid being strong, nitric acid being strong, hydroiodic, HBr, hydrobromic, HCl, hydrochloric acid, and perchloric acid. These are our 6 strong acids. Pause now, write them down on your formula sheet. They're really good to remember. We'll come back over here a little later and talk about our strong bases. But just to highlight, notice what they all have in common. That's a hint about a strong base. So back to our table. When we look at percent ionization, now there is a pattern to this. What the pattern is the strongest acids are on the top of the table, and the weaker acids are on the bottom of the table. So the strength decreases as you go down. So your strong acids are at the top, your weakest acids are on the bottom, your in-between acids are in between. So you can tell by your percent ionization. 100% ionization, right? These are your strong acids. Then we drop. Some people question 51, right? It's greater than 50, right? It's not less than 50%, it's greater than 50%. But we rank it as not a strong acid, okay? The rest are below 50%. Some of them are really far, far below 50%. So you can see the strength of the acid is decreasing as we go. The other thing that's great about this table is your Ka. So we know the Ka for a lot of things. Look at these Kas for our top 6. They're all above 1, right? So all of these Kas are above 1, and therefore these are our strong acids. Products are being favored. The rest of the acids, the Kas, are less than 1, and you can see them dropping quickly. So these are our medium acids, and then at the bottom of the table, we will have our weak acids down there. Okay, so we're going to refer to this table quite a bit, not so much this week, but next week, week 6, we'll be spending a lot of time using this acid-base table. Okay, just wanted to make sure you were there. So when I said that for what was it, acetic acid? Can I find my acetic acid? CH3COOH. Maybe I have to go back, see what I was talking about here. Yes, sorry. Acetic acid, 1.8 times 10 to the negative 5. So if we come back over here and we find 1.8 times 10 to the negative 5, right there. So that's how, right, it lines up with ethanoic or acetic acid. Ethanoic is the traditional name, acetic acid, okay? 1.8 times 10 to the negative 5. So if you think, gee, I wish I had the Ka because it would tell me how strong or weak it was, you can use this table to look for that Ka if you want to, okay? So I know I'm talking fast, but I've got lots to share, and I don't want this to turn into a 60-minute video. So here we have our first setup of Ka. It's our products over reactants. Our products, we know these are going to have equal concentration, so often we'll just say H positive squared. And we are putting it over the concentration, the equilibrium concentration of your acid, okay? So there you go. Ka is found on your acid-base table, so you can find those Kas there, and we're going to be working with them. So 2 methods to determine the strength of an acid. Method 1, percent ionization. It has limitations. It really only works if the concentration of the acid you're talking about is 0.10 moles per liter. And they actually write that right on your acid table so that you don't forget. So here's the fine print at the bottom. The percent reaction of acids with water is for 0.10 molar solutions and is only valid for concentration close to 0.1 Okay, so there is some limitations on that percent ionization, but it's a quick way of determining if an acid is strong or weak. But the more accurate way is Ka. So Ka is the ionization constant for acids, and it's H positive squared over Ha, or over the acid concentration. Okay? Let's try an example. So knowing the value of Ka, we can predict the hydrogen ion concentration and the pH. Here we are, going back to Unit 2, equilibrium. Calculate the pH of a 0.10 mole per liter acidic acid solution as follows. So, using the same equation as before, we calculated the Ka. Now we're going to use that Ka to help us calculate the pH and the hydrogen ion concentration. Okay? So important pieces of information here. And some people have gotten into this habit, underlining numbers so that they can come back and take a look and see which things are going to be helpful. So we have our Ka minus 5, so it's not strong. Okay, we've got a weak Ka, or a weak acid. We are at 0.1 moles per liter. Okay, what can we do with it? We're looking for our H positive concentration, and we're looking for our pH. So moving right along, we're going to be concentrating on writing ionization or dissociation equations. So we want to start thinking about that. Okay, this one's pretty straightforward. We've looked at this before. We're going to take this acid, we're going to take that H away, and then this is what's left over. Okay, we know that these will be equal. It's a 1-to-1 ratio. It's always going to be equal, and we'll talk about that a little later. Even acids that have more than one hydrogen to give, they only give one hydrogen at a time. So it'll always be a 1-to-1 ratio with these two products here. Okay, so that's why we can use the H squared. Here's our equation, H positive squared over our concentration of our acid, CH3COO. Here, if you're thinking about it, if you're visual, think of the green as our CH3COO, and think of the red as our hydrogen. So here is the molecule and a little hydrogen there ready to be ripped away. Okay, so there's two molecules of this. When they dissociate, or when they ionize, the H's, right, they're separate. So they literally separate. That's what we mean by ionization or dissociation. Very important concept, and we'll talk a little more about that. So, rearrange, right? We're looking for H positive here. Why? Because the H positive will allow us to find our pH. So if I rearrange the equation, H positive, the concentration of H positive is going to be the square root of my Ka multiplied by the concentration of my acid. Get away with me, and I'm sure you guys can handle that. Okay, calculate it. It's going to be 1.3 times 10 to the negative 3 moles per liter. Important to put the unit there, okay? Important to put the unit there. You might have used X here. If you use X instead of H positive, you should always tell me what X equals when you're done. Now, we have calculators, so we now can take our H positive and we can turn that into a pH. So it can be 10 to the negative pH, or whichever way you want to do it on your calculator, okay? Oh, sorry, we have the concentration, so we're going to use negative log concentration, so we can find our pH there. So Ka working just like Keq, so that's why we started with Keq. Ka, we have a weak acid, and you might say, well, why a weak acid? Why is it 2.89? And we're going to talk about that, okay? There's a difference between concentrated and dilute versus strong and weak when it comes to acids. This is a weak acid, but it's very concentrated. So we're getting a 2.82 for our pH. So we will address that in a bit. Okay. Here we have another practice problem. It says a solution of weak acid, exactly 0.5 molars, has a hydrogen concentration of 5.77 times 10 to the negative 6 molars. What is the pH? So, very quickly, review from last unit, put in your concentration, take the negative log of it, and we can get our pH. And our pH is 5.239. Reminder, 3 sig figs here, so 3 places after the decimal here. Difference with sig figs. It says, what is the value of Ka? Here's our general formula for Ka. We can plug in our concentration for H positive. We're going to square it for both our ions. And then we can put our 0.5 here, and we get our answer for Ka. Okay? So practice, practice, practice. I'm going to finish this one. I'm already at 30, and I said I was going to keep my videos to 30. So our 2 videos have become 3. I will come back with a second video, and it's going to continue on our conversation with Ka.